Hi guys, today's lesson is on properties and attributes of polygons. Now, let me explain what that means. Polygons, right? It's pretty much a many-sided figure, right? And how many sides do you need to actually make a figure? Well, it's got to have at least 3 or more. So it's a closed plane figure, again, plane meaning flat, formed by 3 or more segments that intersect only at their endpoints. So if you take a look at this figure that I have right here, you can see it's closed in. It's connected by segments, and that's where they intersect. Those are the endpoints of the segments, also known as vertex points, right? Also known as vertex points. So these are all the sides. Of course, all the corners here are the vertex points. And there's also in here something called a diagonal. Now take a look. A diagonal is going to be a segment that connects two non-consecutive. That means not in a row. Vertices or vertex points. So a diagonal is going to connect from here to here. It can't go to here because that's consecutive, and it can't go over to here because that's consecutive. That's the only one over there that is not consecutive that it can connect to. Okay? All right, we're going to talk more about that in a minute. Now, basically this section is about every single other figure that we haven't talked about yet. Okay? 3-sided figures we know are triangles. 4-sided figures are quadrilaterals. 5-sided figures are the pentagons, 6 sides are the hexagons, 7, heptagon, 8-sided figure, octagon, 9-sided figure is the nonagon, the 10-sided figure is the decagon, and the 12-sided figure is the dodecagon. It's like dos. Think of dos in Spanish and decagon, 2 plus 10. So dodecagon. And the N stands for any number, right? So for example, if I have a 20-sided figure, I would call that a 20gon, right? If it has 20 sides, we'd call that a 20gon. Okay, so when numbers get big, like, pretty much over 12, we just call them, whatever the number is, dash gon. All right, now, we're going to talk about these polygons, okay? These are all different kinds of polygons. We're going to talk about them in general. So basically, a polygon is regular if it has all sides congruent and all angles congruent. That's an extremely important word right there, regular. Has to have all congruent sides and all congruent angles. So we've already learned about at least one regular polygon. And of course, that would be the equilateral triangle, right? So for an example there, our equilateral triangle is one type of regular polygon, okay? The equilateral triangle. Another one would be a square, right? All equal sides and all equal angles. But you can have a regular of any one of these shapes, right? You can have a regular pentagon, a regular hexagon. That's that perfect hexagon, that perfect 6-sided figure, that when you see a hexagon, like that's a perfect hexagon when it has all equal sides there, and it would have to have all equal angles. That's what regular means. Now, there are basically a couple different types, basically 2 types of polygons. We have convex and we have concave. Okay, a polygon is convex if all the diagonals, that means any diagonal you can possibly draw, stays on the inside of the polygon. Okay, so if you take a look at this, here is an example here. They're both convex. This one's regular because it has all equal sides and all equal angles. This one is irregular. Yes, all the sides are equal, okay, but you do not have all equal angles. So that makes that irregular. Okay, so again, difference between regular and irregular. All equal sides and angles. Over here, and this could be anything. It's just any other figure that does not have all equal sides and all equal angles. It has to have both. Okay, this is also irregular. Again, you do not have all equal angles. You do not have all equal sides. So again, you see that this figure is irregular. Now, concave versus convex. Convex, as I said, where all the diagonals stay inside the figure. So if I start trying to draw diagonals, you can see they all stay inside the figure. Right in here, they all stay inside the figure. Concave is where it says if all or part of at least one diagonal, okay? So here's the deal. If you have at least one diagonal or even part of it that goes outside the polygon, the figure is concave. Okay, figure's concave. So for example, on this one, right, I can connect here. Where else can I go? I can go over here. I can go over here. I can go over here. But look at this one. As soon as I go from here to here, that one there crosses outside of the polygon. Anytime you have one diagonal, here's one, that crosses outside, that's considered concave. All right, let's look at some of these examples down at the bottom here. It says, tell whether the figure is a polygon. Okay, now first of all, polygons have to have segments for their sides. You see this curvy part right here? That is not a polygon. So right here, I know that is not a polygon. Since it's not a polygon, I can't even name it by its number of sides. That's not even possible there. Okay, now look at this one. This has 1, 2, 3, 4, 5 sides. 5 sides, if we look up at the list up top, we can see that the 5-sided figure is a pentagon. And yes, it's important to know these. All right, so we know it's a pentagon. Okay, and is it a polygon? Yes, it's a polygon. It is also, we can also add something here. We don't know if it's regular or not. There's no side measures given. There's no angle measures given. But we can also add that it's convex, because if I start trying to put diagonals inside here, they all stay inside the figure, right? They all stay inside the shape. So that is a convex pentagon. Okay, look at the next one. This has got 1, 2, 3, 4, 5, 6, 7. That has 7 sides right there. Okay, 7 sides. So if we take a look at the 7-sided figure, the 7-sided figure is the heptagon. Okay, so it's a polygon. Okay, again, it's polygon because they're all segments on the sides. So it is a polygon. It's a closed figure. It's a heptagon because it has 7 sides. And this particular figure, let's take a look. We know it's not going to be regular. We can kind of even see that already. You've got little short sides here, and all these sides are unequal. That would be irregular. Again, they really should give us some markings to determine that, okay, for sure. But one thing we do look at is when we start putting diagonals in here, right, you start putting diagonals. For me to go from this to this, I just crossed outside of the figure right there. Just crossed outside. As soon as it crosses outside, it becomes concave. So that's a concave heptagon right there. And this one, as we said, because it's got a curvy side, that's not a polygon at all. So we can't answer any of these other questions because it's not a polygon to begin with. Okay? All right, let's go on. All right, taking a look up at the top here, this is where we're going to determine if these figures are regular or irregular. Again, if all the angles are marked equal and all the sides are marked equal, it's regular. This, no, not regular. So that we would call irregular. And we can see that if we start trying to draw diagonals in here, they are all going to stay inside the figure. So that would be a convex polygon. Okay, look at the next one. It's got all the sides marked the same. It's got all the angles marked the same. So that polygon is regular. And that's a regular triangle, right? And we know that a regular triangle would be an equilateral triangle. We already know that name for that. Okay, so that's equilateral triangle. And let's take a look at concave or convex. Well, you can't even draw a diagonal. There's no way to draw a diagonal inside of a triangle because all the vertex points are consecutive. Right? There's no non-consecutive. This one comes after this one comes after this, right? So there is nothing there that is a diagonal. So, of course, in that case, it would have to be convex. Okay, it would have to be convex. All triangles, in fact, are always convex. Let's look at the last one. All the sides are not marked the same, so we know that that's irregular. And all the angles are marked the same, but that doesn't matter because if all the sides are not marked equal, it's still irregular. You have to have all equal angles and all equal sides for it to be regular. Now, let's take a look at this. All right, I can already see, right? This is a 1, 2, 3, 4-sided figure. That's a quadrilateral. But if I try to draw a diagonal that goes from here to here, right there, you can see it goes outside. That's concave. Concave figures, guys, are going to cave in, okay? It's anything that's going to cave in. This figure right here caves in right about there, so you can see that it's going to be a concave figure. All right, now, this is an important theorem that we're about to talk about. It's called the polygon angle sum theorem, okay? Basically, what this formula does is it allows you to find the sum of the interior angles of any figure. Let's face it, we already know that a triangle has 180 degrees. Okay, what this formula does is it allows us to say what every single figure in the world, how many degrees all the angles should add up to. Okay, it states that the sum of the interior angle measures of a convex polygon, it's going to be by this formula, n minus 2 times 180. N is our number of sides there. Okay, n is the number of sides. Super important. We have to know what that n represents. So in this case right here, our number of sides is 4. So we're going to plug into that formula, that n minus 2 times 180 right there. That is going to be 4 minus 2 times 180. So 2 times 180, that means we're going to get 360 degrees for a quadrilateral. So all quadrilaterals, including this one right here, that angle plus that angle plus that angle plus that angle, all those angles right there will add up to 360. All quadrilaterals will have a sum of 360. All right, let's look at the hexagon. 6-sided figure, right? 6 sides. 6 minus 2, right? That's 4 times 180. All right, so we just do 4 times 180. And what do we get there? Well, let's see. That's going to be 720. Okay, that's going to be 720 there. All right, next one's the decagon, the 10-sided figure there. All right, so let's look at this one. 10 is the n, that's the number of sides, minus 2. Okay, so that's going to be 8 times 180 is going to be 1,440. Okay, that's a big number, but that's how many degrees all the angles inside of any 10-sided figure is going to add up to, 1,440. Okay, now, you can find out what each angle is going to be if the polygon is regular. So, for example, look at this triangle up here. In this triangle right here, we know all triangles have 180 degrees. We know that. Okay, and we also know that since it has 3 equal angles because it's regular, we would take 180 divided by 3 and we get 60. We already know that all of these angles are 60. So basically, what did we do? We took the sum, right, and we divided by however many angles there were. Well, that's exactly what we're going to do for all the shapes. Okay, take a look at this. If a polygon is regular, then you can divide the sum of the interior angle measures by the number of sides. Okay, so here's how this works. We take the sum of the interior angle measures, whatever the sum is. So in this case right here, these were all of our sums. We would take the sum and we would divide by n. Okay, so down in here, here's the same problem, the quadrilateral. So I'm going to do it down here. Our sum, we said, was 360. I just brought that number down here. Okay, we already did the sum. N minus 2 times 180 was the sum. Now we're going to take that sum and we're going to divide it by the number of sides, which is 4. So the formula is always sum divided by n. That's what we're going to do. So 360 divided by 4. That answer is 90. So each angle in a regular quadrilateral, now again, this is super important. You have to have this be a regular polygon or this doesn't work. And by regular polygon here, if you think about it, what kind of quadrilateral, what kind of 4-sided figure has 4 equal sides and 4 equal angles? Well, we mentioned that earlier. That's the square, right? This has to be our square here. Our square is our regular quadrilateral, and we know that the square has to have 4 right angles, 4 90-degree angles inside. Okay, how about a regular hexagon? Okay, and again, that's that perfect hexagon that I showed you on the other side, that nice little perfect one. What would each one of those nice little perfect angles be in a regular hexagon? Well, you need the sum, which we found up here. That was our 6 minus 2 times 180, right? For this formula, we're doing n minus 2 times 180. So that's what this is. We got 720 up top there. So now what do? We take the sum, the 720, divided by n. And n in this case, the number of sides is 6. So 720 divided by 6 is going to be 120 degrees. So that nice, perfect, regular hexagon where all the sides are equal and all these angles are equal to each other, that is going to be, each one of those angles will be 120 degrees. Okay, so our actual formula, the sum divided by n, is n minus 2 times 180 divided by n. That's the sum divided by n. That's what this actually is that we are doing right here. N minus 2 times 180 divided by n. So, again, we're doing this part first. We had that answer up here, 1,440. So we're taking that sum of 1,440 and we're dividing it by 10. And in that case, we get 144. Okay? So this last one here, let's take this from scratch. All right, let's do this one from scratch. First of all, the dodecagon has 12 sides. Okay? First part of the formula says that we need to take n minus 2 times 180 because that's what we have to do first. So if we do 12, 12 is our n. I'm going to plug that in there now. 12 minus 2, of course, that would be 10. times 180. So 10 times 180 there. What do we get? Let's see. 10 times 180, right? You're going to get 1,800. 1,800. So that's our sum, and we're going to divide it by n, and n is 12. So when we divide that number by 12, we get, oh, something's not right there. Did I do that correctly? Let's see. Divided by 12, 150. That's right. Okay, 150 degrees for that. All right, let's continue. Okay, let's continue. Okay, last part. Now, what we just talked about was for all the interior angles. Now we're going to talk about the exterior angles. All right, now this formula is actually quite simple. This is talking about outside angles. So let me just draw a picture a little bit down here at the bottom and show you what I'm talking about. So in a triangle, we've already talked about this. We have exterior angles. That right there is an exterior angle. It's an angle that's on the outside. So my question here is, when we talk about this, how many exterior angles are there? Well, there's one at every vertex. I can extend this, and I have one here. I can extend this, and I have one here. And the question is, how much do they all add up to, right? The sum of all the inside ones, like this one, and this one, all would be 180. What do all the outside ones add up to? Well, this theorem tells us that the polygon exterior angle sum for every single solitary polygon ever is always 360, always. So it doesn't matter that you have a triangle, okay? This angle plus this angle plus this angle will all add to 360. If I take a parallelogram, right, and I extend all these angles out, right, I got 1, 2, 3, 4 angles. All of those angles add up to 360. It's for every polygon ever, right? Pentagon. I always think of the pentagon as a little house. Okay, that certainly would not be a regular pentagon, but it's a pentagon nonetheless. It's got 5 sides. All right, so this angle out here, this angle here, this angle, this, and this, all those outside angles now, they have a sum of 360. It doesn't matter. The exterior angle sum is always 360, okay? And that's for every figure. Interior angle sums are different. Remember, for the interior angle sum, you have to take n minus 2 times 180. So for the interior angle sum, that's our n minus 2 times 180. Right? That's that formula. For the exterior sum, it's just always 360 degrees. Okay? All right, now let's go on to the next part. What if we wanted to find out what each one of these angles was? Well, the only way to do that is, again, if the polygon's regular. If I knew what all the inside ones were, right, think about this for a second. If this was an equilateral triangle and all those angles were equal there, each one of these angles here would be 60, right? All those angles in there would be 60 degrees. Now, we have a linear pair right here, so if that angle's 60, that one's 120, that one's 120, and that one's 120, because again, they're all supplementary here. 120 plus 120 plus 120, that all equals, right, 360 degrees. Okay, so if I wanted to find out what each one of these angles was, I did not need to go through all that work. I could simply have taken my 360 and divided it by 3, because I have 3 outside angles. And if I took 360 divided by 3, I would get 120. So to find out what each exterior angle is for each one of these, you just take 360 by however many outside angles there are. Now, here's the deal. The outside angles is the same number as the inside angles. So if I have 3 inside angles, I have 3 outside angles. If I have 5 inside angles, I have 5 outside angles. So I'm going to divide by 5 in this case. And when I take 360 divided by 5, I get 72. So I right now can figure out that all these angles here are 72 degrees. Okay? And again, that's only if the polygon's regular. And this was not a regular pentagon. But if it was, that's what you would get. Same thing would happen up here, right? If this was regular, now this is not regular, but if it was, we could take 360 divided by 4 because we have 4 outside angles. So the formula is, for that, you take 360 divided by n. The sum of the exteriors divided by n. And remember, n is the number of sides. Guys, it's also the number of angles, okay? Think about it. If a polygon has 5 sides, it's got 5 angles. It's got 5 interior angles, 5 exterior angles. So that n can just always be the number of sides, but it also represents the number of angles. It's the same every time, Okay, if you take a look at this picture right here, you can see here's a picture. This is not a regular polygon. I know that because not all these outside angles are equal. In fact, it looks like a scalene triangle, which we know it is because if the outside angles are all different, the inside angles will all be different as well. All those three angles add together to equal 360. And again, it doesn't matter what figure it is. Okay, this one right here says find the sum of the interior angle measure of each convex polygon. Okay, so first off, this formula is talking about interior, sum of interior. So think about this now. We got to go back. Sum of interior formula is n minus 2 times 180. Okay, that's our formula we need. So we have here pentagon first. Okay, so pentagon is 5. So we've got 5 minus 2 times 180 there. 5 minus 2 times 180. So in that case, we get there 540. Okay, because that's going to be 3 times 180, and we get 540 for that. Okay, look at the next one. Same formula. Octagon is 8 sides, right? So we're going to do 8 minus 2 times 180. So that will be 6 times 180, and we get 1,080 for that. So that's 1,080. And again, this is the sum. If it's an octagon and has 8 sides, all the angles would add to 1,080. And here's one more. A nonagon has 9 sides. So again, I'm putting the 9 in. 9 minus 2 times 180 becomes 7 times 180, which is 1,260. Okay? All right, so look at the next part. Now, this one says each interior angle. Okay, that's each inside angle of a regular polygon. Remember, you can't find each interior angle unless it's regular. That's got to go together, or you can't find what each angle on the inside is. Okay, unless they tell you. All right, so look at this one again, pentagon. So the formula for this is going to be the sum divided by n, right? That's the interior angle sum. N minus 2 times 180 divided by n is the formula we're going to need. All right, so let's plug it in. The pentagon is 5, right? So we just did that up here, right? That's going to be 5 minus 2 times 180 divided by 5. The n goes in here and in here. So when we plug that in, 5 minus 2 times 180, and then you're going to divide by 5 again. So you get 108. Okay, these angles are 108. Now a heptagon actually has 7 sides. So again, we're going to plug it in this formula right here. So 7 minus 2 times 180 divided by 7. Okay, so again, we can put that right in our calculator. All right, 7 minus 2 times 180 equals, and then we're going to divide by 7. You divide by the n again, which is 7. We get, now this one's got a decimal. We're going to round that off to the nearest tenth. 128 point, well, that's a 5, but the next number is a 7, so we're going to round that to 128.6. Okay? And this one was a 15-gon. That just means it has 15 sides. So in the formula, once again, you're going to plug it in. 15 minus 2 times 180 divided by 15. So we get 15 minus 2 is 13 times 180 divided by 15, and we get 156 there. So in that answer there, the 15-gon has each interior angle as 156. All right, now look at this last part. Find the measure of each exterior angle. Each exterior. Okay, so again, anytime we're trying to find each, it has to be regular. You got to have it regular or it's not going to work to find each angle. All right, so let's take a look. The formula that we use for this is going to be 360, the sum of the exteriors, divided by n. Okay, so quadrilateral has 4 sides. Remember, n is the number of sides. So we're simply going to do 360 divided by 4, and that answer is 90, which makes sense. Regular quadrilaterals are squares, right? If you have a square and all the inside angles are 90 degrees, think about this. All the outside angles have to be 90 as well because they are supplementary. So that makes sense that you have that. All right, and the next one's an octagon. Same thing, 360 divided by n. Right? 360 is the sum of the exteriors divided by 8, which is octagon is 8, equals 45. So each exterior angle of a regular octagon would be 8. Okay, guys, go back and rewatch any part of this lesson. Again, you have certain formulas that go with this that you need to remember. Okay? All right, good luck.